Suppose we took a cascade of two systems whose impulse response is essentially that pulse. What I mean by that is, instead of taking just one pulse, take a cascade of them. So, we suppose we have two systems, each of whose impulse response is essentially a pulse, say of the same width. This is a linear shift invariant system. This is another linear shift invariant system. The impulse response here is essentially a pulse, and the impulse response here too is a pulse, both pulses of the same width, let us say t. We cascade them, and we note of course that together this also forms a composite LSI system. And the impulse response of that composite LSI system is essentially the convolution. And we know that convolution very well. That convolution looks something like this. I hardly need to work it out. This is something very familiar to us from any basic course on signals or systems. The convolution looks like this. Essentially what is called a triangular pulse. Now, we can give this a physical interpretation. You know, when you have this LSI system with an impulse response equal to a pulse, what you are essentially doing is a sample and hold process. So, if an impulse results in a pulse, you are essentially sampling a function at a point and holding it for the duration of that pulse. That is what the physical meaning of that impulse response given by a pulse is. So, if you have two such sample and hold, then you are effectively talking about a triangular impulse response. So, there is some underlying physical meaning. Now, the natural question to ask is, what can we say about the time bandwidth product of this triangular pulse? How bad or good is it compared to the Gaussian? That is the next question that we shall answer. So, the time bandwidth product of this triangular pulse. And you remember that we do not need to worry where this triangular pulse lies. So, we can as well center it and put it at 0. We do not need to worry how wide this triangular pulse is as long as we have kept it symmetric. So, we can put this from -1 to 1, and we do not need to worry what the height is, and we can as well therefore make the height equal to 1. Good. All this is because of the invariance properties of the time bandwidth product. It is invariant to scaling on the dependent variable, it is invariant to scaling on the independent variable, and it is invariant to translation. So, we shall find out the time bandwidth product of this. In fact, we can describe this function. Let us call this function x of t as a function of t and describe it. It is essentially 1 minus mod t for mod t between 0 and 1. So, how would we find the time bandwidth product? We shall first obtain the time variance. And you will recall that since the function is centered, that means the center of x t is at 0. The time variance is going to be described by the norm of t x t, the whole squared in L to R, divided by the norm of x in L to R, the whole squared. Now, we shall be requiring this norm of x in L to R, the whole squared, again and again. So, let us begin by calculating this norm first. The norm of x t in L to R is easily seen to be 2 times integral from 0 to 1 minus t the whole squared d t. This 2 times comes because of the symmetry around t equal to 0. So, essentially the area on the negative and the positive side is the same. Now, this is an easy integral to evaluate. We can easily make the substitution lambda is 1 minus t and evaluate this integral, and that gives us the norm of x t in L to R squared is 2. Again, this is lambda squared. Now, d lambda is minus d t. So, we could write minus d lambda here, but the limits also change from 1 to 0 in that case, and therefore, this is the same as 2 integral 0 to 1 lambda squared d lambda. This is easy to evaluate. This essentially evaluates to 2 by 3. That is easy to evaluate. It is lambda cube by 3 from 0 to 1. Anyway, so much so for the L to R norm. Now, let us take the norm of t x t. So, let us evaluate norm t x t the whole squared. Now, here again we will use symmetry. So, it is 2 times the integral from 0 to 1 t times 1 minus t d t using symmetry, the whole square of course. Now, here it is not going to help very much to make a substitution of variable, because even if we substitute lambda as 1 minus t, we will get a 1 minus lambda here, which is not so convenient. So, let us keep it as an integral in t, and let us evaluate the integral bravely, so to speak. So, that is 2 integral from 0 to 1 t squared 1 minus 2 t plus t squared d t, which is 2 integral 0 to 1 t squared minus 2 t cubed plus t to the power 4 d t. Easy integrals to evaluate, and we do that. T cube by 3 there, t to the power 4 by 4 there, and t to the power 5 by 5 here, evaluated from 0 to 1. And that is 2 1 by 3 minus 2 by 4 plus 1 by 5. Simple enough. Let us simplify a little bit. So, 1 by 15 is what we have. 16 minus 15, that is 1, 2 and 2 cancel, and there you are. Now, this is the L2 norm of T x t squared. I mean the L2 norm of T x t the whole squared in L2R, that is what I mean. So, we have the time variance ready for us. The time variance is therefore one by 15 divided by 2 by 3, which is 1 by 15 into 3 by 2, or that is 1 by 10. Now, let us look at the frequency domain. In fact, the frequency domain will be a little easier, because we are going to make use of the principle of bringing the frequency to the time domain in calculating variance. That is a very easy integral to evaluate. The frequency variance is going to be given by the L2 norm of dxt dt the whole squared divided by the L2 norm of x t the whole squared. And dxt dt is a very simple function to evaluate. In fact, dxt dt has the following appearance. It is interesting, dxt dt here has the appearance of Haar wavelet. And it is very easy to calculate the energy in this. The L2 norm of dxt dt is simply L2 norm squared, I mean, is simply 1 squared into 1 plus 1 squared into 1, looking at the areas of the rectangles. So, that is 2. And we already know the L2 norm of the function squared 2. So, we know this, we know the L2 norm of x, it is 2 by 3, and therefore, the frequency variance turns out to be two divided by 2 by 3, which is 3. Now, we can calculate the time bandwidth product. So, the time bandwidth product is 0.1, the time variance multiplied by 3, the frequency variance. Lo and behold, it is 0.3. So, that is very good news actually, if you think about it. We know the minimum we can go to is 0.25. We have come all the way down to 0.3, pretty good. From infinity, we have come all the way to 0.3, just by cascading the system with itself once again. Not bad at all. So, although there was bad news in the uncertainty principle, that you cannot reduce the simultaneous localization in time and frequency, below 0.25 in the sense of the time bandwidth product. There was good news in that you knew what the optimal function was, namely the Gaussian. Then there was bad news again that the Gaussian was physically unrealizable as a function, but now we have some good news, namely that we can go all the way down to 0.3 by a very meaningful function.